Oh my gosh, we only have 9 minutes left. I think I can get through this. So now we're going to talk about managing risks. With risks, there are hazards. That is the other side of risks. So hazards are the actual bad thing that happens in space. So hazards, how to identify them? They are hazardous conditions, events, or states. You would want to identify the effect of the hazardous state, the severity of the effect, all potential causes of the hazardous states. How would you control for the hazard, the likelihood of each cause, and then verification strategies for the controls. Hazards include collisions or impacts, loss of control. I will not list those all out because we'll go over them in our sample activity. So just photographic memory of that right now. Okay, the other side of hazards are risk evaluation. We have something called a risk matrix, where on one axis there's the likelihood of something happening, and then there's the consequence of if that hazard happened, how bad would it be? So let's say that we have radiation. Radiation is almost certain that it will happen. And for certain components, the effect can be negligible to catastrophic. So FPGAs are pretty resilient to radiation. So we would say that the consequence of radiation hitting an FPGA is pretty moderate, and it would end up as a classified moderate risk. But if it were an extreme critical component, such as a computer, then the consequence would be catastrophic. If a bit flipped and your spacecraft spazzes out, then the risk would be extreme. And at that point, you have to address something extreme. You would have to mitigate that risk by, say, putting radiation protection around your computer. So yes, likelihoods can be formalized into different probabilities. So improbable or rare has a probability of less than 10 to the -6, whereas something that is likely to occur is something that happens more than 10% of the time that you're out there. The consequence ratings, as I talked through my example, range from minimal or no impact to no mitigation approaches at all. So these would require extreme design changes. So let's see, the red zones require new processes or a change in the baseline plan with a 10% or more program budget impact. Excuse me. The orange zone requires aggressive management and the consideration of alternative processes. The yellow zone requires some management actions, and the green zone signifies that the current approach is sufficient. The risky scenarios to manage are a result of hazard analysis. Risk management mimics and follows the design process, where you start out with an initial design that you identify and assess. You then decide and reduce, monitor, and accept. You update the design and you enter this loop again, and you do this iteratively until the final design. Okay, in our last 5 minutes, I'm going to answer the question about where potential sky crane failures for the MSL missions could stand in these different categories. I think it's a good question that illustrates how you would think about a spacecraft mission. So here I have a concept of operations for the entry, descent, and landing of the Mars Science Lab. They call it the 7 minutes of terror because all of this has to be automated. The amount of time that it takes for us to hear back from the lander, the amount of time that happens, the delay would be too long, and this maneuver will have already happened. So for that reason, this maneuver has to happen completely automatically. We typically We engineers typically don't like that because we think that we're very smart and we like to control things. So we have to break down each of these different entry, descent, and landing phases and parse out all of the hazards and mitigate them as much as possible. So in this process, there are temperature extremes. The lander is going to experience extreme heat as all the atmospheric particles are hitting this shield. So we have this heat shield that is used to mitigate that extreme temperature and protect the rover that is inside. Let's see, there are explosives that happen over here where the heat shield is no longer needed and you need to pop the heat shield off so that the radar underneath the heat shield can start collecting data. So a hazard could be that the explosive either damages the rover inside or the heat shield does not come off and we are not able to collect radar data. Other things that can happen, loss of critical function can happen anywhere in the whole automation process. If we lose critical function, then the entire spacecraft will just crash land into the surface. What else? So yep, collision is another thing. We just talked about that. Another hazard is the parachute not deploying or the parachute ripping up. So you can mitigate that hazard by testing the crap out of these parachutes in realistic conditions, like a wind tunnel. You can also make the parachutes much stronger than they need to be, but then that increases in mass, so there has to be a balance. So